Okay, in this example, we will solve for Millman's theorem to understand what would be the equivalent circuit of something of this nature where you have either current voltage or voltage supplies in parallel or current supplies in parallel, okay? So what this means is eventually I will end up with an E equivalent of some form here, and some sort of a resistor equivalent, just like we did with Thevenin, R equivalent, and between point A and B, and then we could have our load connected to this, so RL right here. Now, for Millman's theorem, the important part is to understand how do we find E equivalent and R equivalent. Then from there, we could, for example, once it's found, then we could find, for example, what IL is, if that is a question, or what the VAB here while the load is in place, based on this example, okay? All right, so, so how do we look at any of this? Again, A and B is in here, all right? So the Millman, in a situation like this, let's start with R equivalent, will be equal to R1 in parallel with R2 in parallel with R3. Okay, so that will be the basic solution for R equivalent. And how about E equivalent? E equivalent, right? Now, E equivalent, in theory, should be the sum of all the voltages against their resistor. So it would be E1 over R1 plus E2 over R2 plus E3 over R3 divided by, and here's what's going to happen here, 1 over R1 plus 1 over R2 plus 1 over R3. Except here, we have to make sure that we pay attention to the direction of these power supplies. So in our case, if our ground, let's say, is right here, our reference, well, then E1 is positive, E2 is negative, so minus E2, okay? And E3 relative to ground is positive. So for us, mathematically, if you have to solve this, make sure you put a minus here for that particular situation or that particular scenario. So if this was 10 volts, 40 volts, and let's say 15 volts, then you would do 10 minus 40, and this will be 15. Okay? So that is how you solve for E equivalent, which in this case would be VAB, okay? But you have to understand that's open when it's open. So what is the true IL that you would get here, or the true VAB for example, right? Well, before you do anything, you have to make sure that you're looking at this from a voltage divider rule. So if you have E equivalent here, this is a portion of E equivalent. So VAB in reality here will be equal to E equivalent, okay, times RL divided by R equivalent plus RL. Okay? So that would be VAB at that stage. Okay, so what would be IL? Well, IL, if you're looking at it this way again, it will be E equivalent divided by R equivalent plus RL. Okay? So what would be the power? P will be equal to VAB times IL. Now you could do it that way. Or P will be equal to VAB squared divided by RL. Or P will be equal to what? RL IL squared. Now, how did we get here? Well, you know that this is VAB is RL IL squared divided by RL. So that we can eliminate RL here, so you end up with RL IL squared. Okay? And let me just write it up nicely. So now you know where these come from and how they're evaluated. Okay? So no matter what your scenario, this is how you would pretty much solve for Millman in terms of figuring out what is the voltage between A and B with the load, what is the current load, and what is the power consumed by the load, using any of these possible solutions. If you have VAB and IL, go for it directly. If you only have VAB, go ahead and square VAB and divide by RL, okay? If you have already IL, go ahead and square it and multiply by RL. And that should solve your problem.